Good morning/afternoon, everyone. Welcome to today's presentation. I am Associate Professor Yasser Madany. I'm a senior member of IEEE and a senior member of URSI. Today I will be talking about signals, specifically focusing on digital signal processing, or DSP. Over the next few minutes, we'll explore the fundamentals of DSP, its applications, and its importance in modern technology. I'm excited to share this knowledge with you, so let's get started. Let's start by looking at the introduction to our topic. Here, we'll explore the fundamental concepts behind signals, including standard signals and singularity functions. These form the building blocks for understanding more complex signals we'll encounter later. Next, we'll move on to other basic signals, which expand our toolkit and give us a broader perspective on how signals can behave. Then, we'll discuss the direct formula, a powerful way to represent signals mathematically, providing clarity and precision in analysis. Following that, we'll classify signals into different types. This helps us organize and understand their properties better. We'll also examine how signals change when we transform the independent variable, such as time or space, which is crucial for signal processing techniques. Similarly, we'll look at transformations of the dependent variable, focusing on how changing the amplitude or other aspects affects the signal. Finally, I'll give you an outline of the entire presentation, so you know what to expect and how all these pieces fit together in our overall study of signals. Welcome to the introduction slide. Here, I want to set the stage for what we'll be exploring today. We'll start by outlining the key points that will guide our discussion, ensuring everyone is on the same page. It's important to understand the core concepts up front, as they form the foundation of the entire presentation. I'll explain these points in a way that's engaging and easy to follow, connecting each to the overall theme of our session. This introduction isn't just about overview. It's about framing the importance of what we're about to delve into. So, let's keep these ideas in mind as we move forward. This will help us see the bigger picture clearly. Let's take a closer look at step signal. This concept is fundamental in understanding how systems respond to sudden changes. When we talk about step signals, we're referring to signals that abruptly change from one value to another, which helps us analyze system behavior in a clear and straightforward manner. Next, we have standard signals or singularity functions. These are essential tools in signal processing and system analysis, because they allow us to model complex behaviors with simpler, well-defined functions. For example, the Dirac delta function is a classic singularity function that represents an impulse occurring at a specific moment. Understanding these signals is crucial because they serve as building blocks for analyzing and designing systems. They help us predict how systems will react to different inputs, especially when dealing with sudden changes or impulses. Throughout the rest of this presentation, we'll see how these concepts fit into the bigger picture of system analysis, making it easier to understand the dynamic responses and behaviors we encounter in real-world applications. Now, let's take a closer look at the shifted step signal. This is a fundamental concept in signal processing, especially when we're dealing with systems that respond to sudden changes. Essentially, a shifted step signal is like a standard step function, but it starts at a different point in time, not necessarily at zero. This shift allows us to model real-world scenarios where a change occurs after some delay. Moving on to our next point, we have the standard signals or singularity functions. These are the building blocks for many signals we analyze. Standard signals include impulses, steps, and ramps, each representing a specific type of change or behavior in a system. Singularity functions, like the Dirac delta, are particularly useful for modeling instantaneous events, such as an impulse, which is idealized as occurring at a single point in time. Connecting these ideas to the bigger picture, understanding shifted step signals and singularity functions is crucial because they help us analyze and design systems that respond to sudden or delayed inputs. They form the foundation for more complex signal analysis and are key tools in our engineering toolkit. All right, let's take a closer look at this slide. Here, we're focusing on how to express a given waveform, like the ones shown in the figure, in terms of step signals. This is a fundamental approach because step signals form the building blocks for more complex waveforms. What we're doing is breaking down the waveform into simpler, manageable parts, these step signals, and then reconstructing the original waveform from these parts. Think of it as a kind of Lego building where each step signal is a piece, and together they form the entire shape. Now, in the example, labeled as Example 1, you'll see how this process works in practice. The key idea here is to identify where the steps occur in time and what their magnitudes are. By doing this, we can write the original waveform as a sum of scaled and shifted step signals. This method is powerful because it allows us to analyze and manipulate waveforms more easily, especially when dealing with complex signals. It also ties into the broader theme of our presentation, understanding signals by decomposing them into fundamental components. So, as we go through this example, keep in mind that the goal is to see how the waveform can be reconstructed from these basic step signals, making analysis and further processing much more straightforward. Let's take a closer look at the ramp signal. This is a fundamental type of signal used frequently in control systems and signal processing. It essentially starts at 0 and increases linearly over time, which makes it very useful for testing system responses to gradually changing inputs. Now, when we talk about standard signals or singularity functions, the ramp signal fits right in as a standard signal. It's one of the basic building blocks we use to analyze and design systems. Singularity functions, on the other hand, include things like the Dirac delta function and the unit step, which are more idealized. The ramp signal itself can often be constructed or represented using these fundamental functions, especially in the context of convolution and system response analysis. Understanding the ramp signal helps us grasp how systems respond to inputs that change gradually rather than abruptly. It's an essential concept because many real-world signals resemble ramps or can be approximated by combinations of these fundamental signals. So, in the context of the overall presentation, recognizing how the ramp signal and singularity functions interact gives us a powerful toolkit for analyzing dynamic systems efficiently. Let's take a closer look at the shifted ramp signal. This is a variation of the standard ramp signal, but with a key difference: it's shifted along the time axis. This shift allows us to model signals that start at different times, which is really useful in practical applications. Now, when we talk about signals like these, we often use either standard signals or singularity functions. Standard signals are straightforward, like the ramp we just discussed, but singularity functions, such as the Dirac delta, help us represent sudden changes or impulses in a system. Both approaches are powerful tools in analyzing and understanding complex signals. They give us a flexible way to describe and manipulate signals that might not be as simple as a basic ramp or step. Connecting this to the overall theme, understanding these variations and the functions that describe them is fundamental in signal processing and system analysis. They enable us to model real-world signals more accurately and develop better control and response strategies. Let's take a moment to discuss the notes provided on this slide. As you can see, the notes are meant to guide us in understanding the key points more thoroughly. They help us highlight the most important concepts and ensure we connect these ideas to the overall theme of the presentation. When we present, it's crucial to go beyond just reading the notes. Instead, we should explain and elaborate on them conversationally. This approach makes the information more engaging and easier for our audience to grasp. Remember, the goal is to make the content relatable and clear, so always aim to connect each point back to the bigger picture we're discussing today. Let's look at the solution now. The key idea here is to express the given triangular waveform, like the one shown in the figure, in terms of simpler signals, specifically ramp and step signals. This approach makes analyzing and working with the waveform much more manageable. By breaking down the complex shape into basic building blocks, ramp signals that increase or decrease linearly, and step signals that switch on or off at certain points, we gain a clearer understanding of its structure. In this example, we'll see how to decompose the triangular wave into these components, which is a common technique in signal processing. It's important because it helps us analyze the waveform in the frequency domain and facilitates operations like filtering or system response analysis. So the main takeaway here is that representing complex waveforms as combinations of basic signals simplifies their analysis and connects to the overall theme of understanding and manipulating signals more effectively. Let's talk about the impulse, or Dirac delta signal, which is a fundamental concept in signal processing. This signal is categorized under standard signals or singularity functions. The key idea here is that the Dirac delta isn't a traditional signal in the usual sense. Rather, it's a mathematical construct that helps us analyze systems. It's characterized by an infinitely high peak at a single point, with an area of 1 underneath it. Think of it as an idealized impulse that occurs at a specific moment in time. This makes it incredibly useful for probing system responses because it effectively samples the system at that exact moment. When we use the Dirac delta in analysis, we're often interested in how a system reacts to such an instantaneous input. So, understanding this singularity function is crucial because it serves as a building block for more complex signals and system analysis. It's a perfect example of how mathematical concepts can simplify and deepen our understanding of physical systems. Now, let's take a look at the shifted impulse, also known as the Dirac delta signal. This is a fundamental concept in signals and systems because it helps us understand how systems respond to very short, instantaneous inputs. The Dirac delta is often called a singularity function because it's not a regular signal in the traditional sense. Instead, it's more of an idealized mathematical construct. What makes the delta function so interesting is that it's zero everywhere except at a single point, where it's infinitely large, but in such a way that its total area under the curve is exactly 1. This property makes it incredibly useful for analysis, especially when dealing with system responses. When we talk about a shifted impulse, we're essentially moving this delta function along the time axis. This shift allows us to analyze how a system responds to impulses occurring at different moments in time. It's a powerful way to understand the system's behavior in a very precise and mathematical manner. Overall, the Dirac delta and shifted impulses are key tools in signal processing because they help us break down complex signals into simpler, fundamental components, making analysis more manageable and insightful. Now let's take a closer look at the notes for this slide. Here, the focus is on explaining the key points thoroughly, but in a way that feels conversational. I want to highlight the most important concepts to ensure they stand out. As I do this, I'll connect these points to the overall theme of the presentation, making sure everything feels cohesive and meaningful. The goal is to make the content engaging and clear, so that it resonates with the audience and reinforces the main messages we're trying to communicate. Today, I want to introduce you to the impulse, or Dirac delta, signal. This is a fundamental concept in signals and systems. It's often considered a standard signal or a singularity function. The key idea here is that the impulse function is like a spike at a specific point in time, with an infinitely high magnitude but an area of 1 under the curve. This makes it incredibly useful for analyzing system responses because it effectively samples a signal at that exact moment. When we talk about singularity functions, we're referring to these idealized signals that help us understand how systems react to very short, instantaneous inputs. Recognizing and working with the impulse signal is crucial because it forms the basis for many analysis techniques, like the convolution integral. It connects deeply to the overall theme of understanding how systems respond to various inputs, especially those that are instantaneous or highly localized in time. So, grasping the impulse function unlocks a lot of powerful tools in signal processing. Let's take a closer look at the shift in the unit doublet signal. This shift is quite important because it helps us interpret the environment or the molecules we're studying. The unit doublet signal itself is a fundamental concept, showing how two closely spaced peaks can tell us a lot about coupling constants and the surrounding electronic environment. Now, beyond the unit doublet, there are other basic signals that you should be familiar with. These signals form the foundation of what we analyze in spectroscopy, and understanding them allows us to piece together the bigger picture of molecular structure and interactions. Throughout this presentation, we've been emphasizing how these signals relate to each other and how variations, like shifts, can reveal subtle details. Recognizing these patterns and differences is key to mastering the interpretation of spectral data. So, keep in mind that whether we're looking at a simple doublet or more complex signals, the core principles remain consistent. It's all about understanding how the signals reflect the molecular environment. Now, let's take a moment to review some notes that are really important for understanding the key points on this slide. These notes help us clarify the main ideas and ensure we're all on the same page. As we go through, I'll highlight the most critical concepts and connect them back to the overall theme of our presentation. This way, the information stays relevant and meaningful, reinforcing how these details fit into the bigger picture. Remember, these notes are here to enhance your understanding, so feel free to keep them in mind as we move forward. Let's take a closer look at some fundamental types of signals. First, we have the sinusoidal signal. This is perhaps the most important because it forms the basis for understanding more complex waveforms. Sinusoidal signals are characterized by their smooth, repetitive oscillation, which can be described using sine or cosine functions. They are essential in many applications, from communications to signal processing. Next, we have the exponential signal. These signals are characterized by their exponential growth or decay over time. They are crucial in modeling natural processes like radioactive decay or charging and discharging in electrical circuits. Exponential signals help us understand how systems evolve over time, especially when the change is proportional to the current state. Finally, we have other basic signals. These include a variety of simple waveforms such as step functions, pulse signals, and ramps. Each of these has unique characteristics and applications, serving as building blocks for more complex signals. Recognizing these basic signals allows us to analyze and interpret a wide range of real-world signals effectively. Connecting all these, understanding these basic signals is fundamental to grasping the broader concepts of signal analysis and system behavior. They serve as the foundation upon which we can build more advanced understanding in the field of signal processing. Now, let's take a closer look at the gate signal, also known as the gate function. This is a fundamental concept in digital electronics, especially when working with signals that control other parts of a circuit. The gate signal essentially acts as a switch, allowing a signal to pass through only when certain conditions are met. It's crucial for controlling timing and synchronization in digital systems. Moving on to other basic signals, these are the foundational signals that form the backbone of digital communication. They include signals like the clock, reset, and enable signals, each playing a vital role in ensuring that our digital circuits operate correctly and efficiently. Understanding these signals helps us grasp how complex digital systems coordinate and function seamlessly. By mastering the gate signal and these basic signals, we build a solid foundation for designing more advanced digital systems. They are the building blocks that enable precise control and reliable operation across a variety of applications. Now, let's look at the solution approach. We synthesize the given waveform into a single half-sine waveform, as shown in the figure. This means we take the complex signal and approximate or represent it with a simple, smooth half-sine shape. This approach allows us to analyze and understand the waveform more easily, especially when dealing with power calculations or signal processing. The key here is that by using this half-sine waveform, we can simplify the analysis while still capturing the essential characteristics of the original signal. This method is quite powerful and is often used in practical applications to model or approximate more complicated waveforms effectively. So, in essence, we're using a straightforward, well-understood waveform shape to represent a more complex signal, making our analysis both manageable and insightful. Another solution. Let's explore an alternative approach to addressing the challenges we've discussed. This slide highlights the importance of thinking creatively and being open to different strategies. It's crucial to remember that no single solution fits all situations, so having multiple options allows us to adapt more effectively. By considering this alternative, we can often find more innovative and efficient ways to achieve our goals. Connecting this to the overall theme, staying flexible and resourceful is key to overcoming obstacles in any project. So, keep an open mind and always be ready to explore new solutions that might better serve our objectives. Let's take a look at the direct formula. This is a straightforward way to approach our calculations or problem-solving steps. The key idea here is that the direct formula allows us to find the answer quickly by plugging in our known values. It's especially useful when we want to avoid unnecessary complexity. Remember, the most important concept is that it provides a clear, concise method to link our variables directly, saving us time and reducing potential errors. Connecting this to our overall theme, understanding and applying the direct formula helps us work more efficiently and confidently in practical situations. Now, let's look at the solution. We start by synthesizing the waveform as shown in the figure, using a standard signal. Essentially, this means combining basic waveforms to recreate the desired signal. For this example, labeled as example 4, the key is to understand how these simpler signals come together to form the complex waveform. This approach is fundamental in signal processing because it allows us to analyze and generate signals efficiently. By mastering this synthesis process, we can better understand how signals behave and how to manipulate them for various applications. So, keep in mind that the core idea here is breaking down complex signals into manageable, standard components. Let's look at the solution here. We synthesize the waveform as shown in the figure by using step functions. Essentially, this means breaking down the complex waveform into simpler, manageable pieces. These step functions, which can be added together to recreate the original signal. In this example, number 5, we see how this method is applied in practice. The key idea is that by approximating the waveform with these steps, we can analyze or generate signals more easily, especially in digital processing or simulations. This approach is fundamental because it connects to the broader theme of how we handle complex signals by decomposing them into simpler building blocks, making analysis and synthesis more straightforward and more precise. Now, let's take a closer look at continuous time and discrete time signals, as well as how we classify different types of signals. Understanding these distinctions is fundamental to signal processing. Continuous time signals are functions that are defined for every instant in time, meaning they have a value at every point along the time axis. Think of something like an analog audio waveform, smooth and uninterrupted. Discrete time signals, on the other hand, are only defined at specific time intervals, like samples taken from an analog signal at regular intervals. This distinction is crucial because it influences how we analyze and process signals in different systems. When we classify signals, we're essentially categorizing them based on certain properties. For example, some signals are deterministic, meaning we can predict their values precisely if we know their behavior, while others are random or stochastic. Signals can also be classified as energy signals, which have finite energy over time, or power signals, which have finite power but infinite energy. Recognizing these classifications helps us determine the appropriate processing techniques and system design strategies. Throughout this presentation, you'll see how these classifications form the foundation for understanding complex signal behaviors and their applications across various fields. This framework allows us to approach signal processing systematically and effectively. Now, let's talk about even and odd signals, which are fundamental concepts in signal classification. These classifications help us understand the symmetry properties of signals, which is crucial for analyzing and processing them effectively. When we categorize signals, we primarily look at their symmetry about the vertical axis. For example, an even signal is symmetric, meaning if you reflect it across the vertical axis, it looks the same. Mathematically, this means that the signal satisfies the condition ft equals. On the other hand, an odd signal is antisymmetric. If you reflect it about the vertical axis, it changes sign. In other words, it satisfies the condition that ft equals minus. Understanding whether a signal is even, odd, or a combination of both helps us simplify many analysis tasks, such as Fourier transforms, because these properties influence the frequency domain representation. Recognizing these properties ties back into our overall theme of signal analysis. By classifying signals, we gain deeper insights into their behavior and how best to process them. Now, before we move on, I want to draw your attention to this note. It's important to understand that the content on this slide is meant to clarify some key points. As we discuss, I'll be explaining these points thoroughly, but in a conversational way, so it feels natural and engaging. I'll also highlight what I consider the most important concepts to make sure they stand out. And of course, I'll connect these ideas to the overall theme of our presentation, so everything fits together and makes sense in the bigger picture. Keep this in mind as we go through, and don't hesitate to ask questions if anything isn't clear. Let's take a closer look at even and odd signals and how they relate to signal decomposition. When we talk about decomposing a signal, we're essentially breaking it down into two fundamental parts, the even part and the odd part. These components are important because they help us understand the symmetry properties of signals. The even part of a signal is symmetric around the vertical axis, meaning it looks the same when you flip it around the y-axis. On the other hand, the odd part is antisymmetric. It changes sign when reflected around the y-axis. Recognizing these parts allows us to analyze signals more effectively, especially when dealing with Fourier series or transforms, because many signals can be expressed as a sum of their even and odd components. This decomposition not only simplifies complex analysis, but also connects to the broader theme of understanding signal behavior and properties in the frequency domain. So, by mastering the concepts of even and odd signals, we're better equipped to analyze and process signals in a more structured and insightful way. Now, let's look at the solution for this part of the analysis. The key task here is to find and plot the even and odd parts of the signal, as shown in the figure. Essentially, we're decomposing the original signal into its symmetric and antisymmetric components. This helps us understand the underlying properties of the signal better. By visualizing these parts, we can see how they contribute to the overall shape. This approach is fundamental in signal analysis because it simplifies the study of complex signals by breaking them down into more manageable pieces. So, when you see this figure, remember it's a visual representation of this decomposition process, making it easier to analyze and interpret the signal's behavior. Let's continue exploring the solution. On this slide, I want to emphasize that addressing these challenges requires a comprehensive approach. It's not just about implementing a single fix, but rather integrating multiple strategies that work together. For example, investing in advanced technology can significantly enhance our capabilities, but it needs to be paired with proper training and process improvements. Another key point is the importance of collaboration across teams. When different departments work together seamlessly, we can identify issues more quickly and develop more effective solutions. Lastly, I want to tie this back to our overall theme, sustainable growth. By focusing on these integrated solutions, we're setting ourselves up for long-term success, ensuring we're adaptable and resilient in a changing environment. Let's look at this solution carefully. We are given a discrete signal, which we'll call xn, and our goal is to find its even and odd parts. Now remember, every signal can be decomposed into these two fundamental components, its symmetric and antisymmetric parts. The key here is to understand how to mathematically extract these parts. The even part, xen, is symmetric around the y-axis, so it satisfies xen equals xen. The odd part, xon, is antisymmetric, meaning equals negative xon. To find these, we use the formulas. The even part is half the sum of xn and xn, and the odd part is half the difference between xn and xn. Once we compute these parts, it's really helpful to verify our results visually. That's why plotting xn, along with its even and odd components, gives us a clear picture of how well our decomposition works. In this example, by applying these steps, we reinforce the fundamental concept that any discrete signal can be broken down into symmetric and antisymmetric parts, which is a powerful tool in signal analysis and processing. Let's take a closer look at this notes slide. Here, I want to emphasize that these notes are meant to support and enhance the main content of our presentation. They serve as a guide to help clarify key points, ensure we cover everything important, and keep the flow smooth. Think of them as our talking points or reminders to keep us on track. As we go through, I'll highlight how these notes connect to the overall theme, reinforcing the message we're trying to deliver. Remember, the goal is to communicate clearly and confidently, making sure the audience understands the core ideas and their relevance. So, keep these notes in mind as a helpful tool to make our delivery more effective and engaging. Let's now take a closer look at periodic signals, which are fundamental in signal processing. A periodic signal is one that repeats itself at regular intervals over time. This repetition makes it predictable and easier to analyze. For example, a sine or cosine wave is a classic example of a periodic signal. In contrast, we also have unperiodic signals, which do not repeat in a regular pattern. These can be more complex and are often seen in real-world scenarios, like speech or natural sounds. Now, understanding the classification of signals helps us grasp their behavior and how we can manipulate or analyze them. Signals can be broadly categorized based on various criteria, such as whether they are continuous or discrete in time, and whether their amplitude is continuous or discrete. This classification is crucial because it influences the methods we use to process these signals. Recognizing whether a signal is periodic or unperiodic, and understanding its other characteristics, forms the foundation for designing systems that can effectively handle them. Overall, grasping these key points about periodic and unperiodic signals and their classification helps us build a solid understanding of how signals behave, which is essential as we delve deeper into signal processing concepts. Let's now explore the classification of signals, focusing on periodic and unperiodic signals. These are fundamental concepts that help us understand how signals behave over time. Periodic signals repeat their pattern at regular intervals, which makes them predictable and easier to analyze. Think of a sine wave. Its shape repeats consistently over time. On the other hand, unperiodic signals do not have a repeating pattern. They are more irregular and can vary unpredictably. Recognizing whether a signal is periodic or unperiodic is crucial, because it influences how we process and interpret it within various systems. Throughout this presentation, understanding these classifications will be key to grasping more advanced topics in signal analysis and communication systems. Let's take a closer look at periodic signals. When we talk about a periodic signal, it means that the signal repeats itself after a certain interval, which we call the period. For example, if the fundamental period m equals 1, that indicates the signal repeats every unit of time. Now, an important point here is that the period is tied to the fundamental frequency of the signal. It's also essential to understand the difference between periodic and unperiodic signals. Periodic signals repeat consistently over time, while unperiodic signals do not have a repeating pattern. This classification helps us analyze and process signals more effectively, depending on their behavior. In summary, recognizing whether a signal is periodic or unperiodic helps us determine how to handle and interpret it in various applications. This classification is a foundational concept that connects directly to the overall theme of understanding signal behavior and processing techniques. Let's walk through how to determine whether signals are periodic or not, both in continuous time and discrete time domains. The key here is to analyze each signal carefully. If a signal repeats itself after a certain interval, that interval is called its fundamental period. If no such interval exists, the signal is aperiodic. when a signal is periodic, identifying the fundamental period is crucial because it characterizes the signal's repeating pattern. In this example, number 8, we'll apply these principles step by step. First, look at the mathematical form of each signal, then check if it repeats over some interval. For continuous time signals, we look for a real number t such that the signal equals itself when shifted by t. For discrete time signals, the process is similar, but t is an integer. Remember, the most important concept is recognizing the repeating nature of the signal, which often involves examining the signal's frequency components or mathematical form. By understanding whether a signal is periodic, and, if so, finding its fundamental period, we gain deeper insight into its behavior and how it interacts within systems. This understanding is essential in signal processing and system analysis, tying back to the overall goal of designing efficient and effective communication systems. Let's explore the fascinating topic of periodic and unperiodic signals, focusing on the conditions that determine whether the sum of two periodic signals is also periodic. When we add two signals that are periodic, an interesting question arises. Under what circumstances does their sum remain periodic? This is crucial because understanding this helps us analyze complex signals built from simpler periodic components. The key point here is that for the sum of two periodic signals to be periodic, their fundamental periods must be related in a specific way. Typically, this means that the ratio of their periods should be a rational number, which allows us to find a common period that repeats for both signals simultaneously. If their periods are incommensurate, meaning their ratio is irrational, then their sum will not be periodic. Recognizing this condition helps us predict the behavior of combined signals in various applications, reinforcing the overall theme of signal analysis, how basic properties influence composite signals. Let's talk about the least common multiple, or LCM for short. For example, if we consider the LCM of 2 and 4, we look at their multiples. The multiples of 2 are 2, 4, 6, 8, 10, 12, and so on. The multiples of 4 are 4, 8, 12, 16, 20, 24, and more. The key idea here is to find the smallest number that appears in both lists. In this case, that number is 4, which is the LCM of 2 and 4. Now, in the context of signals, determining the LCM helps us find the fundamental period of combined signals. So, the solution involves identifying the fundamental periods of the individual signals, if they are periodic, and then calculating their LCM to find the overall period. This process is crucial because it tells us when the composite signal will repeat itself, which is essential in analyzing signal behavior and synchronization. And that's how the least common multiple ties into understanding periodic signals and their fundamental properties. On the other hand, random signals have uncertain values, which means their behavior can't be precisely predicted at any given moment. Instead, we usually describe these signals using their statistical properties, like averages or variances, to understand their behavior better. Now, a signal is considered deterministic if its value at any point in time can be exactly defined by a specific mathematical equation. So, for example, a sine wave with a fixed amplitude and frequency is deterministic because we can write down its formula and know exactly what it's going to be at any moment. When we look at signals in general, we classify them into two main categories: deterministic signals and random signals. This classification helps us understand how to analyze and process different types of signals in various applications. Now, let's take a closer look at energy and power signals and how we classify them. Understanding these classifications is essential because it helps us analyze signals based on their characteristics and energy content. When we talk about energy signals, we're referring to signals that have finite energy over time, meaning their total energy is limited. On the other hand, power signals are those with finite, non-zero power, which usually extend over an infinite duration. Recognizing whether a signal is energy or power is important because it influences how we process and interpret it within our systems. This classification ties back to the overall theme of analyzing signals to optimize communication, control, and processing systems. So, grasping these fundamental differences sets the stage for more advanced signal analysis techniques. Let's now explore the classification of signals, starting with energy and power signals. Understanding the distinction between these two types is fundamental because it helps us analyze and process different signals effectively. Energy signals are those that have finite energy over all time, meaning if you integrate the square of the signal over its entire duration, the result is a finite number. On the other hand, power signals have finite, non-zero average power over time, which typically means they extend infinitely in time but maintain a consistent power level. Recognizing whether a signal is an energy or power signal allows us to determine the appropriate tools and techniques for analysis. This classification ties into the overall theme of signal processing. Understanding the nature of signals is crucial for designing systems that can handle them efficiently. Let's take a closer look at energy and power signals. These are fundamental concepts in signal processing that help us understand how signals behave over time. When we talk about energy signals, we're referring to signals that have a finite total energy, meaning the integral of their squared magnitude over all time is finite. Think of it as the total amount of signal present. On the other hand, power signals are those that have a finite, non-zero average power over time, which means their energy is infinite, but their average power remains bounded. This distinction is crucial because it influences how we analyze and process different types of signals. Recognizing whether a signal is energy or power helps us determine the appropriate analysis techniques and system design strategies. Overall, understanding these concepts ties back to our goal of effectively analyzing signals and designing systems that can handle various signal types efficiently. Now, let's take a moment to review the notes for this slide. As you can see, the key points here are focused on explaining the main ideas thoroughly, but in a conversational manner. The goal is to highlight the most important concepts so that they resonate with the audience. It's also crucial to connect these points back to the overall theme of the presentation, ensuring that everything fits together cohesively. Remember, the aim is to make these complex ideas accessible and engaging, so feel free to use a friendly tone and keep the flow natural. This way, the audience can follow along easily and stay engaged throughout the discussion. Let's look at the solution approach here. First, we need to check whether the given signals are energy signals or power signals. This is an important step because it helps us understand the nature of the signal. Energy signals have finite energy over all time, while power signals have finite and non-zero average power. Next, we calculate the energy and power for each signal. Calculating the energy involves integrating the square of the signal over all time, which gives us a measure of the total strength of the signal. For power, we look at the average value of the signal's squared magnitude over a period or over all time, depending on whether the signal is periodic or not. By doing these calculations, we can classify the signals correctly, which is essential for analyzing their behavior and applications in systems. This method applies broadly, whether we're dealing with simple or complex signals, and helps us understand the fundamental characteristics of the signals we're working with. Alright, so when approaching signals, the first step is to check whether they are energy signals or power signals. This distinction is crucial because it determines how we analyze and interpret their behavior. To do this, we need to calculate the energy and power of each signal. Energy signals have finite energy over all time, meaning their total energy is limited, while power signals have finite average power but potentially infinite total energy. In this example, number 11, we'll walk through the process of identifying the type of signal and then calculating its energy and power accordingly. This approach helps us better understand the signal's characteristics and how it behaves within our system. So, by systematically checking and calculating, we can accurately classify signals, which is fundamental for designing and analyzing communication systems effectively. Let's continue exploring the solution, picking up where we left off. As we delve deeper, it's important to understand how these strategies build upon each other to create a comprehensive approach. The key points here emphasize not just the individual components, but how they work together to address the challenges we've identified. By focusing on these interconnected elements, we can develop more effective and sustainable solutions. Remember, this aligns with our overall goal of creating a more resilient and adaptable system. So, keep these connections in mind as we move forward, because understanding the bigger picture is crucial to implementing successful solutions. Let's now look at the conditions that define non-causal and causal signals. A non-causal signal is one where the amplitude is positive for both positive and negative time instances. In other words, it has non-zero values before and after the origin, meaning it depends on future values as well. This is important because non-causal signals are not physically realizable in real-time systems, but they are useful in analysis and processing. On the other hand, a causal signal is one that has zero amplitude for all negative time instances. It only exists for zero and positive time, which makes it practical for real-time applications. If a signal is causal, it means it depends only on present and past values, not future ones. Understanding these distinctions helps us classify signals effectively. Causal signals are fundamental in systems that operate in real time, while non-causal signals often appear in theoretical or offline processing contexts. Both classifications are essential for analyzing how signals behave and how systems respond to them, tying back into our overall theme of signal analysis and system design. Now, let's take a closer look at the classification of signals, specifically focusing on analog and digital signals. These are fundamental concepts in understanding how information is transmitted in communication systems. Analog signals are continuous in nature, meaning they can take any value within a range, which makes them ideal for representing real-world phenomena like sound or light. On the other hand, digital signals are discrete, consisting of specific values or levels, usually represented as binary zeros and ones. Recognizing the differences between these two types of signals helps us understand their applications and advantages. For instance, analog signals are more susceptible to noise, but they can carry a more natural, detailed representation of information. Digital signals, while more robust against noise and easier to process, require conversion from analog signals in many cases. This classification is a key part of the overall theme of communication systems, highlighting how signals are categorized and managed to optimize transmission and processing. Let's explore the concept of time reversal, or reflection, in the context of transformations of the independent variable. Essentially, this involves flipping the graph along a specific axis, which can reveal interesting symmetries or behaviors in the function. When we reverse time, we're reflecting the graph across the vertical axis, which can help us analyze how the function behaves when the input values are negated. This kind of transformation is especially useful in understanding the symmetry properties of functions, and it connects directly to the overall theme of transformations and their effects on graphs. By examining how the graph changes under time reversal, we gain deeper insights into the function's structure and characteristics. Let's explore the concept of time reversal, also known as reflection. This involves transforming the independent variable in a function. Essentially, we're flipping the graph over a vertical line, which means replacing the variable t with t. This kind of transformation can reveal interesting symmetries and properties of the function. By doing this, we're looking at the behavior of the function as if time were running backward. It's a powerful tool because it helps us understand how the function responds to such reflections, and it connects to the overall theme of transformations in our analysis. So, when we perform this change, we're essentially reflecting the graph across the vertical axis, giving us insight into the time reversal symmetry of the system we're studying. Let's talk about time shifting, which is a key concept when we discuss the transformation of the independent variable. Essentially, this involves shifting the entire function along the time axis. By doing this, we're changing the point in time at which the data or the system's behavior is observed, without altering its shape or form. This is particularly useful when we want to analyze how a system responds to inputs at different times, or when aligning data sets that are out of sync. It helps us understand the dynamics more clearly by viewing the same pattern from different time perspectives. In the broader context of our presentation, understanding time shifting allows us to manipulate and interpret signals more flexibly. It's a fundamental step in modeling, analyzing, and controlling systems, especially when dealing with real-world data that might not be perfectly aligned in time. So, in summary, time shifting is a powerful tool for transforming the independent variable, giving us a new way to look at the data and gain deeper insights into system behavior. Now, let's talk about time shifting, which is a fascinating aspect of transforming the independent variable. Essentially, this involves changing the timing of our data points or signals to analyze how shifts in time impact the behavior of our system. It's like moving a graph left or right to see what happens to the pattern. This technique is especially useful when we're trying to understand causality or delay effects. By shifting the independent variable in time, we can examine how past or future values influence the dependent variable. This concept ties directly into the broader theme of our presentation, which is about understanding and manipulating variables to better interpret complex data. Remember, time shifting isn't just about moving data around. It's a powerful tool for uncovering hidden relationships and dynamics within our models. Now, let's move on to the concept of time scaling, which involves the transformation of the independent variable. Essentially, this means we're changing the way we measure or represent time in our model. By doing this, we can often simplify the analysis or better understand the system's behavior. For example, instead of looking at raw time, we might scale it to a different variable that highlights certain dynamics more clearly. This transformation can reveal insights that are not immediately obvious in the original time scale. It's a powerful tool because it allows us to manipulate the time axis to fit the problem at hand, making the overall analysis more flexible and insightful. This idea ties directly into our broader theme of how we can modify and adapt our models to better capture real-world phenomena. Let's talk about time scaling, which is a powerful transformation of the independent variable. Essentially, this involves changing the way we measure or interpret time in our models. By transforming the time variable, we can simplify complex equations or reveal underlying patterns that weren't obvious before. It's like zooming in or out on the timeline to better understand the dynamics at play. This technique is especially useful when dealing with differential equations, as it can help us normalize or standardize the problem, making it easier to analyze and solve. So, in the broader context of our presentation, time scaling is a key tool that allows us to manipulate the independent variable to gain deeper insights and improve our modeling effectiveness. Now, let's talk about the combined transformation. This involves transforming the independent variable, which is a key step in many analyses. Essentially, we're applying a transformation to the original variable to better meet model assumptions or to linearize relationships. This can include common transformations like logarithmic, square root, or reciprocal transformations. The goal here is to improve the fit of the model and make the data more manageable. It's important to understand that combining transformations can sometimes reveal patterns or relationships that weren't obvious before. So, by transforming the independent variable, we're adjusting our data to enhance the overall analysis and ensure more reliable results. This step connects directly to our broader theme of making data more interpretable and models more accurate. Let's talk about amplitude scaling now, which is a key transformation of the dependent variable. When we apply amplitude scaling, we're essentially adjusting the size of our data's fluctuations or variations. This is often done to make different datasets more comparable or to stabilize the variance. For example, if one dataset has much larger amplitude than another, scaling can help bring them onto a similar level, making analysis easier. It's a straightforward but powerful way to improve the interpretability of your data. Remember, by transforming the dependent variable through amplitude scaling, we're enabling more meaningful comparisons and more robust modeling. This step fits into the overall theme of data transformation as a means to enhance the clarity and accuracy of our analysis. Let's talk about addition as a transformation of the dependent variable. When we perform an addition, we're essentially shifting the entire data set by a certain amount. This means that every value of the dependent variable is increased or decreased by a fixed number. This kind of transformation is useful because it can help us meet the assumptions of certain statistical models or make the data easier to interpret. Importantly, adding a constant doesn't change the shape of the distribution or the relationships between variables. It simply moves everything up or down on the scale. This connects to the overall theme of transformations because our goal is often to adjust the data in ways that make analysis more valid or insightful, without distorting the underlying patterns. Let's talk about multiplication as a transformation of the dependent variable. When we multiply the dependent variable by a constant, it effectively scales the data. This means that the entire set of values stretches or shrinks, depending on whether the constant is greater than or less than 1. It's a simple but powerful way to see how the relationship between variables can change. This transformation is especially useful when we want to adjust the units or interpret the effects more meaningfully. For example, multiplying by 100 might convert a decimal into a percentage, making the results more intuitive. Overall, understanding how multiplication transforms the dependent variable helps us grasp how different manipulations can influence the shape and scale of our data, which is key in both analysis and interpretation. This ties back to our overall theme of understanding relationships and making meaningful adjustments in our models. Let's take a moment to explore the concepts of running integration and running sum or accumulation. These are important techniques used to understand the total change over a period, especially when dealing with data or signals. Essentially, they help us see how values accumulate over time, giving us a clearer picture of overall trends. Next, we'll look at first differentiation and the first difference. These are methods to analyze how a variable changes from one point to the next. Differentiation in a continuous sense, or the first difference in discrete data, allows us to identify the rate of change. This is crucial for understanding the dynamics of the system or data we're studying. Finally, we'll discuss the transformation of the dependent variable. This is a powerful tool that involves modifying the variable we're analyzing to better reveal underlying patterns or to meet certain analytical assumptions. Transformations can make data more normal, stabilize variance, or linearize relationships, which ultimately enhances our analysis. Throughout this section, the core idea is how these techniques can help us interpret complex data by simplifying or highlighting key characteristics, all while connecting back to our overarching theme of understanding system behaviors through transformation and analysis. Let's take a closer look at the convolution, integral, and convolution sum. These are fundamental tools in analyzing systems, especially when dealing with linear time-invariant systems. Essentially, they help us understand how an input signal is transformed by a system to produce an output. Now, a key concept here is the transformation of the dependent variable. When we talk about convolution, we're really looking at how the system's response is built up by combining the input with the system's impulse response. This involves integrating or summing over all the past inputs, weighted by the system's response at each point. The convolution integral applies in continuous time, where we integrate the product of the input and a shifted, time-reversed impulse response. Conversely, the convolution sum works in discrete time, summing the products over all relevant discrete points. Understanding this transformation is crucial because it allows us to predict the output of a system based solely on its impulse response and the input signal. This ties back to the overall theme of control systems and signal processing. By mastering convolution, we gain powerful insight into system behavior and response. All right, let's walk through this solution together. We start by defining our signal of t, with the condition that x at t equals 0 for all times t less than 3. This essentially means that the signal is inactive before t reaches 3. Now, the key part here is to determine, for each given signal, the specific values of t where we can confidently say the signal is 0. Since our initial condition states that t is 0 for t less than 3, any signals that are only active after t equals 3 will be 0 before that point. When analyzing these signals, I want you to pay close attention to their support, meaning the intervals where the signals are non-zero. If the signal's support starts after t equals 3, then it must be 0 for all t less than that starting point. So, in essence, the most important concept here is understanding how the initial condition x of t equals 0 for t3 constrains the values of t for which the signals can be 0. This approach helps us determine the guaranteed 0 intervals by linking the signal's support to the known inactive period. Remember, this kind of analysis is fundamental when working with signals, especially in the context of systems where initial conditions influence the behavior over time. So, always look for the support of the signals and how it relates to the given initial condition. All right, let's continue exploring the solution. As you can see on this slide, we're diving deeper into the key points that support our overall approach. First, it's important to understand that each point builds on the previous one, creating a comprehensive picture of how our solution effectively addresses the challenges we've discussed. By thoroughly explaining these concepts in a conversational way, I want to make sure the ideas resonate and are easy to grasp. The most critical aspect here is recognizing how these elements work together to reinforce our strategy and ensure success. Connecting these points to the overall theme is essential, reminding ourselves that every detail contributes to the bigger picture of achieving our goals. So, as we move forward, keep in mind how each piece fits into the broader context and supports our mission. All right, let's take a look at the solution. We start by defining our signal xn, which is 0 outside the range from n equals -2 to n equals 4. That means for any n less than -2 or greater than 4, xn is guaranteed to be 0. Now, when we're given different signals, our task is to determine the specific values of n where these signals are guaranteed to be 0 based on this initial information. In this example, we're focusing on understanding the bounds of where the signal can be non-zero, and consequently, where it must be 0. This is a common theme in signal processing. Knowing the support of a signal helps us analyze and process it more efficiently. So, when you look at any given signal, think about these bounds and use the initial conditions to pinpoint the 0 regions. This approach is fundamental in understanding the behavior of signals, especially when dealing with systems that rely on limited or finite support. Thank you all for your attention throughout this presentation. If you have any questions or want to discuss further, please feel free to reach out to me. My email is contact@imadany.com, and you can also contact me at Dr. Yasser, Madany@yahoo.com. Additionally, I'm available through Madany at IEEE.org. For more information about my work and projects, please visit my website at https://imadany.com. Once again, I sincerely appreciate your time and engagement. Thank you.